As we work with solving problems that have forces in them, you're going to find that there's a couple basic types of problems that you're going to see. And we actually already covered one in the last video that was on something being pushed or pulled at an angle on the ground. So that's kind of, you'll see that problem type a lot. In this section, we're going to look at tension problems. So I'm going to take you through a problem solving process on how you go about solving a tension problem. So here's my problem solving strategy, and I'll go step by step through these 4 steps as we actually solve an example problem. So you always draw a force diagram first, and that's true for any force diagram or any force problem that you ever do. You have to start with a force diagram. Anytime you see a force at an angle, you always break it up into x and y components. And once it's broken up into x and y components, you aren't going to use the given force anymore. You're only going to use the component forces as far as in the math part of the problem. Number 3, you're going to sum the forces in each direction. That's going to give you an equation that lets you fill in numbers and then solve for variables. And then number 4 is just to go ahead and solve. So we're going to walk through each of those steps using the example that I have next. So here my example is just to find the tension in the string. This is a very common problem type that you'll see in physics. So we've got a 20 kilogram object hanging down from a string, and they give us the angle that it goes to the ceiling with. So first up, we draw the force diagram. Now remember, the rule for tension is that the tension force always follows the string. So here our force diagram is actually going to look very similar to the picture itself. So first we've got gravity down. Now that's the only thing that you couldn't see on the diagram, but then the tensions is what you did see. So we've got tension 1, tension 2, and the gravity force down. So I'm going to go ahead and sketch in then the horizontal, so that would be the ceiling, or just I guess the whatever you would say would make that horizontal line to get the 40-degree angle from. And then we've got everything that we need to know to solve the problem. So we can go ahead and start looking at the forces that we're given. So in this case, we have 2 forces at angles. So the very first thing that we should do, oh, and I skipped that part, and in this case, because they're the same angle, they are going to be the same size of the force. So the first thing that you do whenever you see a force at an angle is break it down into its x and y components. Now, it's always my preference, although it's not a necessity, but I always like to make my triangles off the horizontal. The reason I do that is so that I can use my handy dandy component shortcut, hypotenuse sine theta for y, hypotenuse cosine theta for x, to find the components. So you could make a different triangle if you wanted, but this is the one that I would recommend. So when we do that, we break that up into x and y components for each one. Now you'll notice here that I leave off the f, so I don't end up with ft1y, because that just seems really seems a little bit bulky there. So I leave off the f and just do t1y. That's enough. That's already kind of a big label for that. So x and y components good, because we have the 40 degrees to the horizontal. That's going to be the same 40 degrees in there. If you don't see that, if I looked at the top angle there in the triangle, I would say that's 90 minus 40 would be 50, and that leaves that the angle that I labeled 40, that's why it has to be 40, because that's going to have to, those 2 angles would have to add up to 90 degrees. So when I do that, because they happen to be the same angle, that's going to tell me that my ty components are the same and my tx components are the same. And really, this is the wonderful thing about solving equilibrium problems, is that you're going to find that you have a lot of things that are equal to each other. You'll also find out that you have things that will add up to be 0. So those are the concepts that we use to solve equilibrium problems. I can't say that today. So the next step was to sum the forces in each. Man, I'm really okay. So the next step is to sum the forces in each direction. So we're going to get the x components, the sum of the forces in the x direction, and then the sum of the forces in the y direction. So in the x direction, I've only got t1x and t2x, and when I sum those together, they have to equal 0. The reason I know they have to equal 0 is because the object is not accelerating. Remember, when I say not accelerating, that might mean it's not moving, so it could be stationary, or it could be moving at a constant velocity. So anything that is not accelerating has to have the sum of the forces equal to 0 in each direction. So for my y direction here, I've actually got 3 forces. I've got the t1y, the t2y, and the fgy. When I add all 3 of those together, it's going to equal 0. Now notice that once I've broken up my initial forces into x and y, I don't put them in the equation anymore. I only use the x and y components in my equation. Okay? Number 4, so I'm going to solve for the forces required in the problem. So from this point, you have to look at the forces that you're given and see which one of those is going to help you solve the problem. So in this case, because they gave us the mass, that means they actually gave us the weight, which is Fg, because mass times 9.8 is the weight. So I'm going to use some of the forces in the y direction to solve. The opposite could be true. They could give you an x component, or an x component force, and you can use that to solve. So it just depends on which number they give you in the problem. So here, since we know gravity, the force of gravity, we're going to use that to find what the tension in the wire is. So looking at my sum of the forces in the y direction equation, I can say that the two y components are equal to Fg. Now in this case, they happen to have the same angle, and because they have the same angle, that means that the two y components have to be equal. So that's kind of handy. So I can say that twice of ty, so since they're the same thing, 2ty is going to equal minus Fg, and I only have the minus there because I subtracted it over. So then when I go ahead and put the number in, I've got my negative 196. That is taken from 20 kilograms times 9.8. So if you want to find the weight of something, mass times 9.8 gives you that weight, and it's negative because it's down. So when I do that, I can go ahead and solve then for ty, and my Ty is going to be 898 newtons. So that's as simple as a tension problem is. You look and see which things are equal to each other or add up to become zero, and you use that to solve the problem they're asking you for. So the tension's not always, you can have strings in different directions, maybe horizontal or at different angles, but other than that, this problem type, they're pretty much all the same. So when you see a tension problem, this hopefully will help you look at how to work through it. So, oh, and I didn't put the, yeah, I'm sorry, I'd only solved for Ty there. So if I want to go ahead and solve for tension, so I know my Ty, sorry about that, and I go back and solve for tension, that's where I'm going to use trig. So the sine of 40, sine is opposite over hypotenuse, so I know that Ty is 98. So if I use my sine of 40 equals 98 over t, then I have the tension. Sorry about that, I thought I was done, but I was not done. So that's where you get the tension from. So the tension is the same in T1 and T2, and that's how you solve a tension problem.